The menu for this video is a change of level. We are going to try to go a little bit more into the technical details, take a peek under the hood. We're not going to go very deep, right? But the idea of this video is to give you an understanding of why things happen the way that they happen when you call a function. So we're going to jump into the code right now and just do a quick little program that calls a method named appropriately do something. So void do something, I'm going to take care of the prototype up here, and then I'm going to define this method, this function, sorry, below the main. Void do something, and you know what? Just a printf working on something. All right, so basic stuff. I just want to call a function, get it to execute, and then come back to the main and display, for example, main function is done. There we go. So do some work with a call to a function, then come back, then do some more work. All right, GCC. Fatal error, greetings.h, no such file or directory. I thought I cleaned up everything since the last video, but apparently I did not. Messy. There we go. I removed those greeting.h include that have nothing to do with our current video. And then hit out. Working on something. So I call the do something method function successfully, and then come back to the main function is done. So what happens exactly when we do this kind of stuff? So when we call any function in C and many language, okay? So the first thing you need to understand is that when a program is loaded by the operating system and executed, it runs inside what is called a process. And a process has a memory space. So it has a view, if you will, on the memory available for it to do its work. And that memory space is actually divided in two zones. So we have one zone, and we're not going to go and look at all of the zones, okay? But just to provide a rough approximation here, we have one zone that we're going to refer to as a heap. The heap is a contiguous zone in memory, okay? And we're going to use it to allocate space to store things. So things means mostly variables, right? So we are going to allocate space, that means reserve space inside the heap to say, for example, I want to store this or that variable. Well, to take a concrete example, if in my program here I have a variable int global 1, okay? I don't know why I called it global 1. I don't think I'm going to need a bunch of them. This is a global variable for the file, for this file, okay? For the file main.c. So when I have something like this, where is this global variable going to be allocated in memory? It's going to be allocated in the heap, okay? So all global variables are going to have, there is global here, they are going to have some space reserved only for their usage inside the heap. And I can store here, for example, the value 42 if this is what I want to put in global. So going back here, global equal 42, here we are. And then I can use that variable, that global variable, from anywhere, any function in this file. Okay, we already went over this. So what else goes in the heap? We talked last video actually, about static variable that go inside functions. So for example, static int counter equals 0, and I'm going to say that this is a variable that I'm going to use to count how many times this function was called. And every time you call it, the first thing it does, it says counter plus plus. And maybe later I'm going to display it or something like that, but for now it doesn't matter, okay? So global variables go into the heap. So when the program starts, at the very beginning when it's loaded, some space is carved in that area of memory to store the value of the variable global, but also the value of the variable counter. Okay, and counter starts at 0. All right, so we have a location in memory that is there to store pretty much global variable. And I'm going to represent the memory as a continuous ribbon, okay, of space, bytes, where I can store things. So the heap is located somewhere there. Okay, fine. And then there is another area of memory that is relevant to this course. There are two, actually. One, we are going to refer to it simply as the text segment. Okay, the text segment is where the code of your program lives. So, when you compile the code, you compile it, you store it in an executable file. When you run that executable file, the operating system is going to read the code, the actual code that has been compiled of your program, and load it in memory into the process address space. Okay, so that's where it goes. It lives there, and we're not going to touch that at all. Okay, we're going to leave it. It's read-only anyway. It's just there for the computer to be able to read the next instruction that has to be executed and go through your instruction like this based on the control flow that you implemented. More interesting for us, there is another area called the stack. And actually, I should have represented the stack as being on the top and growing downward, and the heap being at the bottom. But it doesn't matter. This is not like an accurate diagram of what's happening in memory here. This is just to help you understand the concept. So what is happening in the stack? So when we start the program, there's going to be some information already stored in the stack. When I enter the main method, which is at the very beginning, right? This is the first thing that I do, actually. I enter the main method when I start executing my code. So the moment I start executing my program and it's ready to run and I enter the main method, I'm going to take a chunk of memory here. And I'm going to call it the mains activation, I'm going to abbreviate, record. Okay? Or like in our textbook, for example, it's abbreviated stack frame. So what is a stack frame? That just means that we are going to grow the area that is called as a stack. Okay, we're going to say, okay, it's growing and I need this much space. This much space for what? For the main method, the main function, sorry, to be able to do its job. So this is the memory space that is reserved for the main function to do its job. Some of it is kind of beyond our control. For example, there's going to be some space here that's going to be reserved for the return address in memory. Okay, when you call do something from here, from line 9 in the main, right, you are going to jump to another location inside your text segment, right? You are going to say the next instruction is at memory address, blah, blah, blah. And this is a memory address where the code for do something is actually starting, for example. Well, when you jump there, you execute all the lines of code that are inside the method do something, and then when you reach the end of the method, you need to return to whoever called you. And you may have been called by the method main, or maybe I have another method do something else. Okay, I'm going to write it right now to illustrate. Maybe I have another method called void do something else. So let's do some cut and paste here to implement it fast. There we go. And that do something else method, its only job is going to be to call do something and display some stuff on the screen. I'm calling do something. All right, call do something. With that typo is better. I should compile this because I have a feeling that I have introduced maybe a bunch of typo. I'm done calling do something. Okay. And then I would call do something else, for example, on the main as well. So look at let me compile first. Let me make sure that this is actually proper code. Okay, that's okay. If I run it, looks like it's doing what I expected. Awesome. All right. So the reason for which I made this example a little bit more complicated is I want you to understand that when I start execution here. I call the method do something. So I'm going to jump to the instruction that starts the body of the code for do something. And I'm going to execute all those instructions. And when it comes time to return from the method, from the code function, this is why we call it returning, okay? When it comes time to exit the execution of the function and return to whoever called me, I need to keep track that I was called from this memory address, okay? So all of this code lives in the text segment, and all of those lines of code, all of those statements have actually an address at which they are stored in memory, right? So when I call do something here on line 10, I should record somewhere that when I'm done executing do something, the next thing to do would be execution of what is at line 11. Okay, so I store the memory address where the instructions starting at line 11 are located. This is what goes in the stack here, the return address pretty much. So I call do something, I execute do something, okay, and then I return to the address that I stored on the stack, and now I call do something else, same principle, I store the address at which I need to return, I enter do something else, and then what? I call do something from inside do something else. So let's go back to our diagram here and make it a little bit more complicated. So the main activation record has a little bit of information, not much actually, okay? It has a little bit of stuff about arguments, which we're not going to talk about, but more importantly, it has a return address. It has a bunch of information here that is pretty much managed by the system to make sure that we can return from the function call, okay? And then what? When the main calls do something, I'm going to put on the stack another activation record. This is the activation record for the method do something. For that call to the method do something, I should say. You'll see why next video. So inside do something, what do I need? Well, I need a return address. I need like a bunch of stuff that is system oriented, right? I don't really care about it in the context of this course. And then inside of do something, I have also well, I don't have anything. I don't have any parameter. I don't have any local variable. So if I had need to store things, like for example, if I had a need here to store int local equal 23, right? If I had a local variable that I was using for whatever reason here, then it would go here on the stack. So all of the local variable, all of the parameter variable that you have in a function, this is where they are stored in memory, okay? Our static int counter from line 19 is here. It's in the heap. It appears when the program starts executing, pretty much. This guy here is proper to do something. So it's only when I call the function do something that I'm going to allocate some space on the stack for that function to be able to work. And as a result of allocating space on the stack here, I'm going to be able to allocating space for all the variables, local variables, sorry, and all the parameters that the function has. For example, in this case, it has only a variable called local 23, local equal to 23, okay? And then what? Do something executes, it does its magic. When we reach the end of a function, we don't need anymore to remember what local was, because it was just a local variable to that function, right? So we're not going to be able to access it again, and if we call again the function, we want a brand new one. So all of this, the activation record for do something, is quote-unquote wiped from the stack. And I put air quotes here because it's not exactly wiped, but okay, this is our first contact with the program's execution stack, with the notion of stack frame, etc. So let's make it a little bit more conceptual and less about the detail. It is, for all intent and purpose, removed from the stack. And we return to whatever return address we had stored in that activation record. So we are now back to line 11, ready to do what? Ready to call the function something else, do something else. Something is going to happen. Do something else, I'm going to create an activation record for do something else, okay? And inside of it, I need my return address. I'm going to need that for all the function I'm calling, okay, maybe some other system-oriented information. Do I have any local variable? No. Do I have any parameter? No to store. So that's it. I don't need that much room, actually. I could just put my bar right here, okay. So this is activation record for the main. This is activation record for do something else. And then what? I execute do something else. It's displaying I'm calling something. Then it calls do something. Well, what happens when you call a function? Every time you call a function, every time you enter the code of a function, you reserve a new activation record. So this is an activation record for do something. Please note that the activation record for do something else, that guy here, is not going anywhere because I'm executing line 26 here. I'm not done executing everything I have to do in do something else. I'm not returning from do something else yet, okay? So instead, I'm going to keep that in memory, and I'm going to, the idea is to push onto the stack, okay? And you can see now why it's called a stack. It's like dishes, right? You push a dish, you push another dish on top. Every time you push more information on the stack, you put it on top of the rest of the information that was there. And when you return from a function, you just remove the activation record from that function, then remove the activation record from the one below when it returns, etc. And it keeps going like that. Okay. At the bottom is the activation record for the first function that executed when your program started, which is the main function. Okay. So I pile on top of here an activation record for do something. Well, we know what that looks like by now. Okay. There is a return address, maybe some other system information here, and then I need some space to store local. And local is going to be initialized. So the space to store local is allocated as I enter the function, as I carve pretty much my activation record chunk of memory there, and then I store the value inside of it. And once I am done executing do something, right, reach line 22, this activation record goes away, and I continue execution at whatever return address was specified here. So my activation record disappears, okay? And where do I find myself? I find myself at the last spot that called the function do something, which was line 26, and I execute now line 27, and I reach the end of do something else. When I reach the end of do something else, I branch back, I return to the address, I execute the instruction at the address specified in my return address. My entire activation record, or stack frame, like they call it in the textbook, goes away. All right. And I find myself where? I find myself to where do something else was called, which was line 11. I'm done with that now. I execute line 12, execute line 13. That stops the execution of my program pretty much. So I return from the main function, and guess what? When I return from the main function, so it's a little bit different here because I don't have like really a return address. This is a main function. This is the first function that started the whole program execution, right? So when I return from it, then I'm just going to tell the operating system, and hey, you know what? I'm done. This program is done executing. It has completed its job. You can clean up my whole memory space. And at that point, yes, the whole memory space is going to be cleaned up. The text segment is going to be cleaned up. The heap is going to be cleaned up. At that point, all of this stuff is going to be cleaned up, and your program no longer runs in the memory of the operating system. Okay, so this is a way to give you a first view of the process. It's not that complicated. Okay, it's not that complicated. It's technical details. Okay, it's a little details, but those little details, if you think about them, they explain to you why variables, local variables that are declared inside a function can only be used in the function, why they exist only for the duration of the execution of the function. So the whole concept of duration of storage for a variable, okay, like the textbook calls it, is fully explained and makes sense once you understand what happens when you call a function and where do functions get the memory that they use to actually work to store the variable they need to store for a certain amount of time, to store their parameters, etc. So we are going to look at another example now, the example of the swap, because it's always very instructive pretty much. So I'm just going to add on top of this, I'm going to say, okay, I have a void swap. It takes two parameters, so this time we're going to play with parameters. So I could write int and int. I don't have to specify the name, even though I told you that I like to do so. Makes things a little clearer in my opinion. Void swap int x, int y, and then the code int tmp. So this example is going to be a little bit more interesting because we have local variable like tmp, we have parameter like x and y. So what happens when we call swap, right? X equal y, y equal tmp. There we go. So quick little swap function that's intended to swap the content of the two parameters, and I'm going to use it wrong, of course. I'm going to say int a equal 10, b equal 20, and I'm going to call swap ab, and I'm going to clean up the other methods. We don't need them. Let's keep the example, focused on what it is that we want to really talk about in this part of the video. So all of this can go away. All right, so I don't have any more global variable. I don't have any more static local variable inside of functions. So my heap is going to be a little sad. It's going to be a little empty, right? But I have to make up for it. I have a bunch of local variable here in the main function as a swap function, and I have actually parameters here for the swap function as well. So, okay, let's use this as an example. Let's make sure it compiles so I don't show you code that is poorly written, right? And run it. Main function is done, so I could display a and b before. Let's go for it. Let's make this example self-contained. Okay, I want to display a is %d and b is %d. All right. And then I want to display, of course, the value of a and b. And then I'm going to do that again before, so I do it before the swap, then I do it again after the swap, okay? And we already saw that in a previous video. The swap is not really doing what you would think it's doing, right? The variable a and b are left completely unchanged in the main. And we're going to review that. So I already gave you the explanation of why this is so, but now we're going to look at it from the stack diagram perspective. So every time you do a diagram of your program's execution stack like this, and you trace through your code, we call that a stack diagram, and it's very useful sometimes to understand what happens and why you have certain properties in the language. Like for example here, when I call swap a and b, it's not going to swap variable a and b, okay? The values inside the variable are passed, they are passed to parameters, the parameters are swapped, but then when we return a and b is not swapped at all, and we're going to see exactly what that looks like in memory at a lower level. So again, I'm going to consider that I have my stack, okay? So I'm not going to draw the heap because I don't think we're going to have like anything useful in the heap segment. The text segment, I'm not going to draw it either. Nothing really to say about it right now. I'm going to start at the bottom with my stack, and I'm going to say, okay, this is the main activation record, the activation record for this call to the function main, and it needs room for a variable a set to 10. It needs room for a variable b set to 20. And I'm skipping also the return address and stuff like that. Okay, all that system information, we're going to just say that it's stored somewhere here, like right at the beginning of the activation record. Not really like super important for the level at which we're looking at things in this video. So I start execution, line 7, line 8, int a equal 10, b equal 20, there we go, they are on the stack. Then printf a is 10, b is 20, no surprise. Call the method swap. So this was the activation record for the call to the method main. This is the activation record for the call to the method swap. What do I need inside the method swap? So first I have a parameter x, I have a parameter y, and I have a local variable tmp. So all of this is going to be allocated on the stack, okay, inside the activation record, the stack frame, depending on how you want to call it, of this call to the function swap. So what happened when I call on line 10 the function swap? So I have two arguments, okay? Those arguments can be arbitrary complex expression. So in this case, they're very simple expression, just the name of one variable each. So how do I evaluate the variable A? I look inside and I get the value, that's it. So A is 10, B is 20. So I'm calling the swap function with the values 10 and 20. And those values 10 and 20, where do they end up? They end up assigned to the parameter x and y respectively. Okay, x is the first parameter, so it gets the value of A. Y is the second parameter, it gets the value of B. And now you see on this stack diagram, right, that when you look at the memory, X, Y, A, and B are really distinct. Okay, there's no questioning. The first two variables live in the activation record of the first call to the main method. The second two variables live in the activation record of the call to the swap method that happens on line 10. And then what about TMP? So the first thing I'm going to do when I run my swap method, so starting line 16, is assign the values that are passed as argument to my parameter x and y. There we go, it's done. Then I'm going to make some room for TMP, assign x to TMP, so that's a 10. Then assign y to x. So x right now is a 10, it's going to become a 20, so I assign the value inside of y to x. So at this point, x and y are both equal to 20. And then y equal TMP, I'm going to overwrite the value 20 inside of y with the value that I first saved that was coming from x. And at this point, I did swap the content of x and y, the parameter x and y. I did a swap, actually. The logic of the code indeed swaps the content of two variables, but I swapped the parameters. I reach the end of my swap function, line 20. What's happening? Well, I'm going to branch back to the return address, right? And my swap activation record here goes away. So all this work that I need to swap the x and y is gone bye-bye. And what I'm left with when I return to the main on line 11, what I'm left with is the activation record for the main contains A and B that have never been changed. They are still equal to 10 and 20 respectively. The last thing that's missing in this picture, in this introduction to the concept of stack, is what happens when I return a value. Well, I'm not going to even do like the stack diagram for that, because this is really not the most important thing. Okay, the most important thing is actually the parameter passing for us, and the fact that we create stack frames or activation records on the stack as we call every function. But I would say the return value is something that is actually copied when you return from your function. When you return from your function, for example, from calling swap to the main, well, swap is a void method, so it doesn't return anything. But if we modify it a little bit and we say, hey, swap is going to return an int value, just for the sake of having a function that returns something, and I'm going to always make it return 1, 2, 3, 4. Okay, 1234. That's it. So just it doesn't mean anything. It's just there to show us, like, okay, we have a function that returns a value. What's going to happen? Well, everything is going to happen exactly the way that we described it until now, right? Except that when I return from the swap function, instead of just branching to the address, the return address, like I explained before, we are also storing temporarily this value 1, 2, 3, 4, right? And we are going to make it available to whatever function called us. So for example, on line 10, when I call the function swap, I could do something like int result equal swap A and B. So when I call this function, once again, once it's done doing its job, it's going to return a value, which is 1, 2, 3, 4, that's going to be made available temporarily to the main, just long enough so that the main can assign it to another variable, or use it in an arbitrary complex expression, or print it on the screen, or do whatever you want to do with that, okay? But this value is going to be made available, and then we can, for example, store it in a variable, a local variable inside the main's activation record. So I hope that you see how those mechanism, okay, explain actually the passing parameter by value, explain when the variable become available, when they become actually stored in memory, when you call a function, the difference between global variable, static local variable inside functions, and local variables inside function and parameters, right? The difference in their behavior comes directly from those mechanisms, okay? Where are they stored actually in memory, and how long are they going to be lingering around in memory for us to be able to use them? As usual, if you have any question, you know where to find us, okay? Office hours, I would say definitely as a priority. Other than that, if you have like a simple question, maybe the forum or Piazza will do the trick. Use those resources. Make sure you do not, just stay with something that confuses you or you don't see why it's useful, etc., and move on with it. In a programming class, it's a very bad idea to just like move on when you don't understand something. Just like, be tenacious, stay with us, ask questions until we convince you that it's useful, and we make you see actually its relevance, and then move forward, and it's going to feel a lot easier to move forward. All right. As usual, thank you for your attention.